G'day everyone, welcome to another Toolbox Tech Talk. I'm doing these a little differently at the moment. These are pre-recorded sessions, but don't feel like they're sort of a bit dull because actually I'm going to be here live answering questions. So anyway, feel free just to jump in there, ask questions in the comments field, and I'll be there to answer them as well. So anyway, for those who don't know me, I'm Glenn Morris from the Smart Energy Lab, and I'm not a bad boy rapper, but it's kind of fun, isn't it, on a Sunday? Here we go. So today, pretty short one. Really, I'm going to focus on what's known as maximum demand calculations. Now, maximum demand calculations are something that you might be familiar with for on-grid installations, where you've got a certain capacity from the grid. You have to consider the number of socket outlets and light fittings and dedicated appliances, etc., and work out what the maximum demand after diversity, MAD, maximum demand, MDAD, maximum demand after diversity. Now, diversity is your friend when you're on grid because basically the grid is an infinite source of energy, well, just about. You're only limited by the capacity of your supply. But I'm going to focus on maximum demand for standalone power systems, where you are definitely limited in capacity. Now, this is a bit of a follow-up from a little explainer that I did earlier in the week on what are the features that I think are important. And in fact, I sourced a lot of these ideas from you guys, which was what are some of the key features that an off-grid inverter must have. Now, one of those, and it's a big one really, is the ability to deal with surge demand. So surge demand is something that's a bit hard to quantify. Looking at an appliance, you can't really tell. The nameplate rating probably doesn't tell you that either. Some of this is to do with just skills and knowledge in the industry, but there is a bit of science behind it. So let's take some real-world examples. What I'm looking at here is a load sheet for a customer. Now, this load sheet really just tells me something about the appliances that they have, and they've got things like compact fluorescent lighting, a refrigerator, a television, a stereo, a computer, a vacuum cleaner, watch that one, a dishwasher, a washing machine, and a water pump. Haha. They're going to probably go together, aren't they? An electric drill, an iron, so some, just a small range of appliances. Now we can look up what their power ratings are. So resistive element appliances like an iron is super easy. It'll just say, 1500 watts. And we know it's going to draw 1500 watts when we switch it on. It may cycle. Beware of that, which is good actually. It may cycle, well I hope it will, otherwise it'll burn your clothes, as it gets up to target temperature. So it'll go on, off, and you hear them clicking away. Something like a light, you turn it on and pretty much, so if it's incandescent lighting, it will be a bit of a surge because until the filament heats up, it's actually quite a sudden inrush, but it's very short-lived. Then you've got something like a refrigerator. Now, a refrigerator is quite a problematic load to understand. It draws quite a bit of energy because it's on 24/7. In fact, as I said in earlier Toolbox Tech Talks, the refrigerator is often the problem load in an off-grid design because it's never turned off. It's not a discretionary load. You don't go, oh yeah, today, bit overcast, the weather's bad, I don't want to start the generator. I think I'll just turn the fridge off and let all my food go off. No, it doesn't happen. So the refrigerator is really the one appliance that from the day it's purchased never gets turned off. Maybe when you move house. Even worse, it gets shuffled out to the shed when the new kid arrives and the new shiny, ice-making, internet-connected, automatic ordering refrigerator turns up and the old fridge goes out to the shed and it often becomes like a secondary fridge. The legendary beer fridge, which is full of beer, therefore it doesn't use any energy, and it's a load that's 24/7. But from a maximum demand calculation point of view, the fridge has got a couple of operations. It's got a compressor for refrigerants. It's got a de-icing function, which is the cyclic defrost or continuous defrost. It's got it might have an ice maker. It might have some interior lights. But actually, the thing that I'm most concerned about generally is the motor itself. Now, if this is a modern fridge, and when I say modern, less than about 20 years old, it'll have a soft start motor, which is great because it doesn't have a high inrush. But if it's a really old cranker, one of those ones you got to use two hands to open the door and it just about flies off the wall, it's probably got a reciprocating compressor which has quite a high startup current. Anyway, how do you find these things out? The compliance label doesn't tell you any of this. It'll just tell you, it might say amps, it might say watts. You can, of course, as I mentioned in an earlier Toolbox Tech Talk, which is linked up here, you can go and check out what the kilowatt hour rating of that fridge is. But once again, those are not the things we're concerned with today. We're concerned with the maximum demand of that appliance that is going to be a demand on the inverter system for a standalone power system. So there's a couple of tools I've got here with me that can be quite useful. Now, one's really an electrician's tool and one's more of a consumer tool. So let's start with a consumer tool. This here, there are many types of power meters out there on the market. I actually bought this. I didn't get given it, so I'm not doing any promo, but it is actually quite a nice product. It's Australian developed power meter. So what's nice about it is you can plug it in. It's got a piggyback plug, so it's got a male on one side, female on the other, and so you can plug an appliance into the back of it. So you plug this side into the wall, and then your appliance that you want to measure into this side, and on the screen it will start showing you things like continuous power that it's using at the moment. It'll log that too, and it'll tell you, I think it's the 100 millisecond surge as something turns. It'll turns on, so it'll show you the peak, it'll show the average, it'll start to do kilowatt hour calculations, which is really great as well, especially for a fridge which cycles. But that peak that it measures is quite useful. So you're kind of measuring the relatively long inrush. So 100 milliseconds is quite long, but it's certainly useful to know what that peak was. So that's kind of like a consumer appliance measuring device. Really recommend this particular one. It's called the PowerMate. Comes in, I think, 3 versions. One with an LCD screen, which is the cheapest option, one with the LED screen, one which has got a 15 amp plug on the end, and all of them do the same job, but to different levels and for different capacities. The other tool, which is more of an electrician's tool, is a clamp meter. Now, this is a clamp meter that can measure the current passing through a conductor. So you actually have to clamp it over a single active conductor. So therefore it is really an electrician's tool because you're going to be in a switchboard. You can't just clamp this around a power cord, which embarrassingly I had tried once and wondered why it always measured 0. It's got to measure one directional flow, so it can only go around one conductor, like the active conductor. This particular model has a button down the bottom here, which says inrush. And if I press the inrush button, in fact, why don't I turn it on for you? If I press the inrush button, it will sit there waiting until it measures a peak and then capture it for me. Now, this is a very short peak, and it's in amps. So I can find out, well, volts as well, but I'm going to put it on amp range, and I put on AC amps because I'm measuring an AC appliance, but it can also measure inrush on DC if you need to. But for our purposes, we're concerned about mostly AC appliances in a home these days, and you're looking at the inrush on the active conductor. So that will be generally measured at the switchboard. So that's a peak that's really useful. What else do we need to know? Well, here's the tricky bit. We need to know the power factor. Now, for those of you not familiar with power factor, there's a wonderful analogy which is about how much froth there is on top of your beer. Now, the way it works, power factor is kind of like froth on top of beer. Beer in a glass is the important bit. It's the bit you enjoy. It's the bit that has a special effect. The froth on top really just stops you putting more beer in your glass. Now, reactive power is rather like that froth. It's extra current that circulates within a conductor that does no useful work. So basically, it's filling up the conductor in terms of its capacity and does no useful work. But it's actually got to be produced. It's got to be there. If you wonder how that can be, well, actually, it gets returned within the circuit, so it's not consumed, it's just circulating. And some of it's lost as heat as well. But reactive power is something that an inverter system needs to supply. Even though it kind of gets it back, it still needs to be able to supply that reactive power as well as the active power. So power factor is a measure of the proportion of active to reactive. A power factor of 1 is 100% active power, which is great. That's what you want. That's what a resistive element will give you. A power factor of 0.9 means that 10% of that energy is actually reactive power, etc. So how do you find out what the power factor of appliance is? Now, some more expensive equipment can measure that. I'm not showing that here, but something like an oscilloscope or a power quality meter can actually measure power factor. If you've got something that's got a fairly consistent load, it's sort of like not varying in its load, you can actually just measure the volts and the amps separately, multiply them together, you're going to get the volt amps. And if you've got a watt meter, you can compare the watts to the volt amps. So that will give you power factor. So basically, watts divided by power factor equals volt amps. So that's the way of finding out the VA. And you can rearrange that equation to find out power factor. So power factor, why does it matter? Because, as I said earlier, it's actually part of the demand that an inverter system in a standalone power system has to deliver. So why am I telling you all this? Well, let's go back to that load sheet where the customer had a bunch of loads. Now, you might be designing a system for a home with some loads that have a high power factor, such as motors, pumps and motors particularly, or fluorescent lighting has a negative power factor, which you might think helps, but probably doesn't. And then you'll have some just regular loads, resistive loads like lighting, heating, and appliances that convert to DC, like a computer basically takes AC, makes DC, pretty close to a very small power factor, a very small reactive component, and all of those appliances could be turned on at any particular time. So from a maximum demand calculation perspective for off-grid, one approach is, and this is the only approach you can use if cost is no objective, is just size it for everything. That's stupid because it's almost impossible to turn everything on in a home, but it's possible to size everything, an inverter system that can run everything simultaneously. But most people want an economical solution. They don't want to oversize unnecessarily. And incidentally, a larger inverter generally has a higher parasitic load. That means it's consuming more energy doing nothing. Because of the the size of the transformer and the power electronics inside it, it may be consuming a significant amount of power, 50, 60 watts continuously. So it becomes part of the load problem as well. So it is kind of good design principle to size an inverter system to do the job that the customer needs, but not too big. How do we know what's the right size? Now, this is once again a budget question, but a reasonable approach, and this is following the principles of our design standard for standalone power systems, AS/NZS 5139, which says that you should consider coincidental loads. Now that means things that come on at the same time, and it can be with discussion with the customer, what's a reasonable expectation. So for instance, some appliances are almost always synchronized. If you have a water pressure pump and you use any appliance that uses water, like a dishwasher or a clothes washer, the chances are they'll both be on at the same time. So your dishwasher might turn on, it'll circulate a bit of water, little pump runs, very small load. The big pressure pump comes on, boom, it comes on with a surge, and I'll talk about surge in a second. And it's also got power factor because it's a pump. Then the water heater comes on in the dishwasher and starts heating water. So there's another 1200, 1500 watts of demand. So the two things together could be quite significant, could be a couple of kilowatts or more. Now, there's one other problem with that is I mentioned the pump. Now, pumps are renowned for having very high surge factors. Now, that's not power factor. Surge factor is that inrush. Remember we talked about measuring inrush? So the surge factor is the amount of instantaneous power that the appliance demands when it first turns on. And appliances that are basically stalled electric motors, like a pump, when it's not turning, as soon as it's energized, the windings are a short circuit, and they are basically drawing a lot of power. So that's a real problem. Anyway, so one of the things that we need to consider is what is that surge, how strong will it be, and how long will it last? And that's where measurement comes in and experience as well. But for many, a pressure pump is the problem load. It will often draw 3, 4, 5, up to 7 times its run power as it starts. So now from a maximum demand calculation perspective, we need to consider not just the coincidental maximum demand of loads, not just the coincidental maximum demand considering power factor, but also considering surge demand. So how do we break this down? We use a table which has got a list of appliances and their power ratings. We can use the same table for doing energy calculations, but we're going to skip that today because we've already done that one. And I think the link's up here. We look at the power times divided by, the power factor, and that'll give us a VA demand, and that's a continuous VA demand. So we can then work out what's known as the 30-minute VA demand. Now, the reason for that is it's within a 30-minute period, it's highly likely that a range of appliances will be running. So the inverter may have a short-term load or high load over a period of about 30 minutes as appliances cycle on and off. And so we call that our VA demand. Then we've got the problem of surging loads and loads that draw 3, 5, 7 times their run power. And so that's our surge demand, which is the absolute peak. And therefore that's the absolute peak that the inverter needs to be able to deliver. So we might, in our design, specify some appliances cannot be coincidental loads. And that comes down to the discretion of the operator. The customer or the end user will decide how those appliances are synchronized. Something like, yes, you can use your microwave oven, you can use your coffee machine, and you can use your toaster, but don't put the dishwasher on and the extractor fan at the same time. Now that might seem a bit intrusive, but really the limit is up to the customer. If they choose to try and juggle those loads and they exceed the surge demand of the inverter, it will shut down. The good news is that most quality inverters designed for off-grid applications, when they shut down, they don't blow up, they just turn off. And so there is a loss of power. It may involve going out and resetting something. Worst case is you might even trip a fuse, circuit breaker, or the main battery isolator or main battery fuse might trip. It's all about how that system's been sized. I'd suggest that's actually a problem. You shouldn't be tripping the main battery fuse just with a surge demand. But there you go. So those are some of the parts that you need to put together in sizing the inverter. So I'd suggest you run through the list of appliances with the customer and go, okay, what are the coincidental loads that we expect will occur, such as the water pump and the dishwasher or the clothes washer, and what are the optional ones, and let's see if it's going to work for us in terms of the size of the inverter that we're going to purchase. So we might choose to have dishwasher, clothes washer, water pump, lights, television, stereo, all including power factor and surge all at the same time. But we exclude the vacuum cleaner. I kind of like focusing on the vacuum cleaner these days. Their power ratings are just going insane. It's almost like, apart from cordless ones, mains powered ones have very, very high power ratings. And because of the nature of their motors, some of them is like what's called a squirrel cage motor, they have very high surge ratings. And so you turn them on and there's a wicked amount of inrush. So it could be something like the vacuum cleaner causes the house to trip off. So if that's the case, and something like a vacuum cleaner is a short-term and discretionary load, you don't sort of let it do its own thing unless you got one of those robot kind of vacuum cleaners. But anyway, and they're battery powered, so they won't really matter. You could say that when we're doing dishes, when we're washing clothes, using the water pump and appliances in the kitchen, we're not vacuuming at the same time. That's a reasonable kind of compromise. That should be in your load sheet that you provide the customer. That decision tree, which you've had a discussion with them about, what are the reasonable expectations of your system? Just remember that from a customer's perspective, they think they've bought something that's just like a normal home, and you're trying to kind of get them into a budget, and they're going to have to experience some limitations on that design. So there you go. That's how you calculate a maximum demand for an off-grid system, considering power factor and surge demand and specifying appliances. Now, before I started recording this, I actually had a question come in on the Solar Cutters page, actually. It was a result of a comment I made to one of the installers there about a generator supplying a interactive inverter. Now, I made the comment that I hope this inverter is connected by fixed wiring as per clause 9.4.2 from ASNZS 4509.1. the 2009 edition, which is actually the latest version. And the comments came back, can you please explain what's meant by that? A lot of customers expect that because they've already got a generator, why should they have to buy another one? Well, actually, they don't have to buy another one. Let's take a step back. What's this all about? Well, the clause, in fact, I've got it here. The clause says, connecting generating set in parallel with an interactive inverter. So the key thing there is interactive inverter. What's an interactive inverter? It's one that can parallel its own inverter function with another source, such as a generator. And that means it's running in synchronization with another source. It also means that energy can flow in multiple directions. It can flow towards the load, and it can flow towards the generator, especially under disconnection. Now, basically, you don't want to send power back to a generator. It'll cause it to stall. But it is possible that when disconnecting a plug-in generator, that there is a momentary reverse feed. And that reverse feed is basically a lethal voltage on some male pins of a socket outlet. So, socket inlet, sorry. So, no, that's the reason. You cannot have a socket inlet that could be potentially live when connected to an interactive inverter and as the act of unplugging occurs. Now, I'll have plenty of people push back on this one. They'll go, oh, no, Glenn, it doesn't happen. We know that there is no voltage. It's instantaneous. The moment you pull that plug out, there is 0 volts on those terminals. That might be true. The problem is there is no test for it. So the inverter, the interactive inverter, doesn't have a test that it has to meet, which states that those pins must be dead within X number of milliseconds. So you're really just trusting the manufacturer, or you're just trusting that you think it's okay. So that's one of the reasons why in ASN ZS 4509 Part 1, we specify that the electrical output of a generating set shall only be connected with an interactive inverter using fixed wiring, permanent fixed wiring, to a dedicated circuit breaker. So it's not a plug, it's not a socket inlet with a extension cord plugged into a generator. The other reason for this is reliability. Now, you may be able to find a perfectly suitable generating set on site. So the customer might already have a nice 10 kVA diesel, and you've got a 5 kilowatt inverter charger, and it'll use that 10 kVA diesel nicely to charge batteries. And it's a plug-in one, which is not permitted, okay? Not permitted. The problem is that the customer may decide that that 10 kVA genset needs to go somewhere else. It's being used elsewhere on a farm, and suddenly they need to charge their batteries. So, I've got that little Honda 2 kilowatt unit there. I think I'll use that and plug it in. But you've already programmed their inverter to draw, 6 or 7 kilowatts from their big diesel, and suddenly they've plugged in a toy, camping petrol-powered generating set, and it's just going to stall. So reliability is the problem there. So two things, safety and reliability are the main reasons, but safety is definitely the biggest one. Now, there are practical workarounds for the first problem, the safety issue. Now, many people have come up with diagrams they've sent me showing combinations of contactors that isolate the socket inlet. None of them will work, but there is a way that can work, which is what's known as a plug-in socket with pilot pins. Now, this is not a very common thing, but actually, if you happen to have an EV, you've probably got a Type 2 connector with pilot pins on it. Pilot pins are non-power pins that are the last to connect and the first to disconnect when you're plugging in and unplugging a socket or installation coupler. And what that means is those pilot pins can operate a contactor which isolates the interactive inverter from another source, from a generator, for instance. And those pilot pins are going to be the last to connect. So as you plug in, there's no paralleling of the generator with the interactive inverter until the pilot pins finally seat home after the power pins. And the reverse happens as you start to unplug. The pilot pins are the first to disconnect. They drop the contactor, isolate the interactive inverter from the socket inlet, and then the power pins come out. So that sequence means that you actually can guarantee there'll be no live parts. But such a piece of equipment is pretty rare to find. I've had a little look around the internet. I think Marichal make one, but these are designed for really high power applications like stage lighting, unplugging under load, and they're expensive. But there are smaller ones, and you will find them actually on your inverter. It doesn't have pilot pins, but it's got another solution. Many inverters actually have a screened to IP4X AC installation coupler. That means you can plug it in, and it's locking often, which is another bonus, so it can't be accidentally unplugged. The male pins are screened, so there's no live parts that can be touched, and it's regularly used on interactive inverters, grid-connected interactive inverters, interacting with the utility grid. So those kind of plug-in sockets do exist, but they're really quite small generally, often only suitable for like 20, 25 amps. So, you can get single and three-phase ones, but from a strict letter of the law, they don't comply with 4509 Part 1. So even though from a practical working point of view, it is a safety feature, but it doesn't solve the second problem, which is the reliability of the design, that the other source might disappear, the generator might go off-site, and a small toy one come and replace it, and therefore it's unreliable. So that's kind of why we've got this clause in 4509.1. It's very poorly complied with from my experience, but there you go. It's just a matter of inspection and maybe an incident, and that becomes a real issue. So thanks for that question. I can't remember who asked it, but that was great. So yeah, that's really what I wanted to cover today. Just talking about maximum demand for standalone power systems, and a little bit about interactive inverters and a generator, and why you need to use fixed wiring. So thanks for watching. Once again, I'm Glenn Morris from the Smart Energy Lab. I run training courses online here every other week. You can catch me at solarquip.com. My training courses are listed there. I do courses in fact, the next one coming up in a couple of weeks, which is the battery crash course. It's Wednesday the 17th and Thursday the 18th of February. It's a crash course for installers really on the new battery standard, AS/NZS 4509. And it's, what did I say that for? AS5139. I've got to get my standards right. The new battery standard is causing a bit of a shake-up in the industry, and I thought I'd just do a crash course on how to be compliant with that standard. It's designed for installers, and I've put it as an evening course. So it's 4:30 p.m. till 8:30 p.m. Melbourne time. It's still Melbourne daylight savings time. So it's 2 days, 4:30 to 8:30. The other two courses I'll be running shortly is one for electrical inspectors or experienced installers who really want to know the full gamut of compliance for solar, inverters, and batteries. It's a longer course. It's over 3 days, and it's 4 hours sessions. And then I've got a really big course which is really aimed at a broad audience. It's for installers of standalone power systems, of hybrid systems, of solar systems. It's also useful to people who are just designers and even to end users. So I've had customers do the course. I've had people building an off-grid home do the course. So there's no requirement that you have a electrical qualification, though a basic understanding of electricity would be useful. You'll probably get more out of that course. Now that's 5 days long, and I'll be running that the 1st to the 5th of March. Each morning, Melbourne time, for 4-hour sessions. So there you go. That's the training courses coming up here at the Smart Energy Lab. They're all online. They're delivered via Zoom. I'll be in my little booth where I do my teaching, and all those are recorded, and I share the recordings afterwards. So a lot of people can't make every day of every session, so I record them and then share them straight away later that day, so they can watch them in the evening if they missed it in the morning. Anyway, that's me blasting on about my training courses. Thanks for attending, and I'll see you at the next Toolbox Tech Talk next Sunday, 2 p.m. See ya. Thanks.